Okay, so some of this is a review of things that you've done in the past. Because you do a little bit of statistics in Algebra 1. I know that. Okay, that's the measures of central tendency that we're going to do again. But then the stuff that follows, the measures of spread, specifically standard deviation, that one you shouldn't have done before. And z-scores, I don't remember if you guys do a little z-scores in Algebra 1. Okay. You know, honestly, our use of z-scores here is that it helps us to understand what a normal distribution is. And that's the next lesson. Oh, and by the way, there's just not enough stuff to drag this out as far as I thought it was going to go. So I'm moving things up one day. The quiz will be next class. The test will be like 2 days earlier. Now, I'm not moving up the 9-week test. I'm just going to give us 2 days to review before it. That's the way that'll go. There's just not enough material for here. I tried as hard as I could to find something that we could do in there. But what's that? Behind? No, we're not behind. That was your other class, not this one. You know, in my old school, see, we didn't go near as fast in the first semester. You know, we would not have started rational functions at all, and that's like a big, hard unit. And we usually would not even start that till the second semester. And we would have been scrambling to get all this stuff done now. But here, honestly, I mean, I made the systems into more of a unit than it had to be. I mean, it could just be like one day if all you're going to do is nonlinear systems. And then this stuff, you know, we're not behind. No way. Okay. So measures of central tendencies. You've done this stuff before, right? Mean, median, mode. What does it mean to take the mean of something? That's it, right? And I'm introducing this notation again because we've done this before. The summation, the sigma notation. So if each data value is an xi, then this is the sum from I equals 1 to 5 of xi. That'll give me x1, x2, x3, x4, x5. What is the median? The median means the middle value, right? You throw out the high and the low, you throw out the high and the low until you got one number in the middle, assuming that these 5 data points were in order from least to greatest, x3. Right? Now, if I put some numbers to this, like given a data set, 1, 2, 2, 3, 4, 5, right? The median now, when I throw out the high and the low, 1 and 5, throw out the high and the low, 2 and 4, I actually don't have one number in the middle, I have 2. So how do I do the median? You take the average, right? You take the mean of the middle 2 numbers, 2 plus 3 over 2, 2 plus 5. And then what does the mode mean? The most common value. So if there is a repeated value in the list, then whichever value is repeated the most, that's the mode. So these data sets give the waiting times in minutes of several people at 2 veterinary offices. Find the mean, median, and mode of each data set. Okay, so office A, find the mean. So I'm going to do it with a handheld calculator that you can't see, so you could do it the same if you want. 14 plus 17 plus 18 plus 19 plus 20 plus 24 plus 24 plus 30 plus 32. And how many data values are there? Looks like there's 9, right? I'm getting 22. So 22. Okay, what's the median? Yeah, I mean, you throw out the high and the low, if it's 9, it's got to be the 5th one in the list, right? So there's the median right there. So that looks like it's 20. And the mode? 24, because it occurs twice. So I mean, which one is probably most representative of that data? I mean, if you wanted to represent how long do you usually wait when you go to that vet clinic? I mean, you can decide for yourself, whether you think mean or median. Probably the mode, definitely not the one you'd want to use. Okay, let's try office B. 8 plus 11 plus 12. Divided by, we said 9. 16. And the median is, so this time there's 1, 2, 3, 4, 5. Okay, there's still 9 in the list, so we're going to have 18. And the mode is 18. So they're much more in agreement for this one. In either case, if all you had to decide on was waiting times, which vet clinic you're probably going to. So that's the purpose of trying to represent, especially large sets of data, with some measure of central tendency, so you can kind of get an assessment of, like, what does it represent. So in this case, you probably want to go to office B. Okay. So when you're calculating the mean, you're going to see two different ways to represent the mean, right? In the book and in the calculator, they use X bar, right? X with a bar on the top means the mean, okay? If you look on the formula sheet, which you're going to have, and if you don't have one, let me know and I'll bring one around. Anybody need a formula sheet? Do you need a formula sheet? You need a formula sheet? I think you guys are okay, right? So look in the middle on the left side where it says statistics formula, and you can see where they use that. It's the second line down. That is the Greek letter mu, pronounced mu, right? Not mu, mu. Okay. Now there actually is a difference between these two, and usually at this level of learning statistics kind of stuff, we really don't pay much attention to it. But usually, I shouldn't say usually, but in fact, they actually mean two different things. So let's say that I wanted to know the average height of everybody in America, right? We wanted to have a measure of the average height of Americans. Okay, here's the thing. Whatever value that is, whatever is the actual average height of Americans, that's mu. Okay. Now, I'm not going to go out and measure every American. I'm probably going to come up with a sample, something that's smaller, that I think is representative of all America, and I'm going to measure that smaller sample. And when I take that average, that's X bar. Okay, mu means it's the population, which usually you don't know. X bar means you did a sample, okay, which you know. So there actually is a difference between them, but we're really going to use them kind of as the same thing in this class. So I'll bet you that most of your teachers don't know that. The only ones that would is if they taught AP Stats, then they would know it. Okay, so you try. Find the mean, median, and mode of this. This is data that gives waiting times in minutes of 10 students waiting for a bus. Okay, so what did you say was the mean? Well, in fact, I shouldn't use that. I should say X bar equals, what'd you get? 7.4. Okay, what was the median? Okay, so in order to do that, you had to put them in order, right? So you had to say 2, 3, 4. 2, 3, 4, 6, 7, 8, 8. Probably gonna miss one. 9, 12, 15. So then you had to throw out, right? High and low, high and low. It's going to be the average of those two right there, 7.5. Pretty close. Okay, and then what is the mode? 8. In fact, you could have more than one mode. You could have no modes. You could have more than one mode. When you have one mode, it's called unimodal, right? Generally, the way it works in statistics is if you have a distribution of data, and if you used a histogram to model it, right? If the histogram has like one peak in the middle, that's the mode, right? And if you would say that your distribution is unimodal and symmetric, it looks about the same on both sides, then you're going to use the mean as the measure of central tendency. If it was instead something like, it's actually getting bigger on one side than the other, then you would use the median if it's not symmetric. So the mode, no. Okay, now measures of spread, which is more what we're interested in now. You did the measures of central tendency in the past. Measures of spread. The first one that we look at is range. You've done that one before, right? The range is the difference between the maximum value and the minimum value in your list of data. The range is easily calculated, but not often used in statistics because it's so easily unrepresentative of the data. Like, let's say I would go back to my, weighting of veterinary at the veterinary office. Let's say that the first set of data for Office A, the mean was 22. The median was 20, I think, something like that. What if the next person comes in and waits 100 minutes, right? Absolutely not representative of everything else that happened before. But if you have to calculate the range between the maximum and the minimum value, it looks like there's a lot of variability in that data, and there's really not. Right? 9 of the values were actually pretty closely packed together. It was just that last one that was bad. So the range, we don't use that often. The interquartile range is something you did before. If you remember in Algebra 1 when you were doing these little guys. Remember what that's called? Right? We needed a box and whisker plot. Do you remember what the middle bar represented? That was the median, sometimes called Q2, right? The median is the middle value, right? That means 50% of the values are to the left of it, 50% of the values are to the right. Okay, now if you go through the lower 50% and find the median of that, that is called the first quartile. That's Q1, that's the left side of the rectangle, right? If I find the median of the upper 50%, that's called Q3. Right, and then the extreme values, what's less than, the lower 25% is here, right? And there's another 25% in both parts of the box, another 25% there. So Q3 minus Q1 is telling you like how wide is that rectangle in the middle. So that is a measure of spread. Like I say, if you didn't have symmetric data, you'd be using the median to be your measure of central tendency, and you'd be using the interquartile range to be your measure of spread. Okay, now standard deviation is what we're going to spend most of the class doing today. So let's find the range for our veterinary offices. Okay, and these are in order, so this makes it even easier. What's the range of Office A? Right, the max is here. And the min is here. So we just have to do 32 minus 14. 18 minutes. Right? These are waiting times in minutes. The range is then in minutes. Okay, this one will be 23 minus 8 equals 15 minutes. So office B not only has shorter wait times, there's less variability. According to this one metric, there's less variability. So you can kind of count on it a little bit more. Right? That's why we do measures of spread. Too easy. Okay, try to find the range for these. I'll give you 2 seconds. Okay. 1, 1,000, 2, 1,000. What is it? The max value was here, and the min value was here. Right, so the range is 15 minus 2, which is 13 minutes. Because those are all measured in minutes. That's our range. That's the reason why I'm emphasizing the units. Okay. So now standard deviation, though, is the most commonly used measure of spread. And it's a very complicated statistic to calculate. Right? It's not the most user-friendly of them all. But go ahead and look at the question that it's trying to ask is, how much variability is there in the data? So look at these 3 data sets that I put there, right? 1, 2, 3, 4, 5, 3, 3, 3, 3, 3, 1, 1, 3, 5, 5. Every one of those, if you calculate the mean, it's going to be 3, right? X bar equals 3. In fact, if I calculate the median, it's going to be 3 for all of them. Does that mean there's no differences in the data? No, there's actually quite a bit of differences, right? Look at the middle set of numbers there, 3, 3, 3. How much variability is there in that data? None, right? If you went out and got another piece of data in that group, you probably expect it to be a 3, right? Because they're all 3s, right? But if you look at the first, everyone's different. Look at the last one. That's a little more spread out than the first. So it's not enough just to know the mean and the median. It wouldn't even be enough to do the range. These two would look the same if I did the range, but they're not the same. So that's why we have to come up with some measure for how this data is spread out. And that measure is called standard deviation. So using that first set of data, right, 1, 2, 3, 4, 5, the mean is clearly 3. Okay. So in order to know how much each one of these data values is different from the mean, let's subtract the data value minus the mean. Okay. 1 minus 3, 2 minus 3, 3 minus 3, 4 minus 3, 5 minus 3. Right? Everyone, -2, -1, 0, 1, and 2. Right? Those are the actual differences between our data and the mean. Okay, but I'm trying not to find the individual differences. I want to know the one metric that is the difference for all the data. Well, what happens if I add these numbers up? The negatives are going to cancel the positives. You're going to get 0. Does that mean there's no spread to this data? Clearly, there's spread to the data. But if all I do is take the absolute differences and then add them up, the positives are always going to cancel the negatives. Okay, so how can we fix that? Okay, well, what we're going to do here is let's square it, right? Because what's going to happen when I square the negatives? They're going to become positive. No more cancellation, right? So I'm using the summation notation to represent this again. I'm going to take the sum from 1 to 5 of xi minus x bar squared. So that's saying this xi this is x1, x2, x3, x4, x5, right? So I'm taking these values here, and every one of them I'm squaring. So now I got all positive numbers. And again, I add them up, and at least they didn't cancel, right? But does 10 look like it's representative of the differences between the data? No, I mean, there's an issue here. The issue is that we just took the sum. That sum would be different if I had 10 data points, right? Or if I had 20 or 30. I mean, it would keep adding. So I need to do something to normalize this to take into account how many data points that I'm adding in there. So let's divide by how many we put in there. I mean, that'll get things, take into account that we actually used 5 different numbers to come up with that 10. So divide by 5, okay? 10 divided by 5 is 2. Is 2 representative of all 5 of those values? Not really. It's a little bit too big. That was the most different that 2 of them were. And it's also, besides the fact that it's probably too big, the units are wrong now. Because I squared this, let's say I was doing this as waiting times, which were measured in minutes. These are all representative minutes squared. So to fix that, the last fix to this is, let's take the square root of that number there. That'll make my minutes squared back to minutes, and it'll take this 2 and make it into a smaller number, 1.4, right? 1.4, you know, somewhere in between the -2 and the -1, a little closer to the you know, if we take absolute values, you know, it's about like right there or right there. That's a little better. Seems a little better. Units are correct. I mean, is there another way we might have dealt with this data so that we didn't have negatives and positives canceling each other out? We do have another function that deals with that. How about absolute value? You know, why wouldn't we have just like said, okay, let's take the absolute value of the differences, and then they wouldn't have canceled each other out, which is fine, and that is a statistic that you can measure. But when in statistics, this one is actually important, the way that it's constructed and the way that it's used with the mean when we do things like normal distributions. So this is kind of a convoluted calculation that we have to do to find standard deviation, but it's necessary. Okay, it is necessary. So let's do one. Okay, first, here's the formula for standard deviation. I think on your formula sheet, you do not have it. Okay. All right, there's the formula, and probably the most significant thing to look at here is we use the lowercase Greek letter sigma to represent standard deviation. Right? We're using the capital Greek letter sigma for summation. We're using the lowercase letter sigma for standard deviation. It's the square root of the sum of the difference between the data and the mean squared divided by the number of terms, the number of data values. Okay. So I'm going to do a calculation of standard deviation. And it seems tedious. It is a little tedious. But in the end, it's really not that hard. So the first thing, there's all my data values. This is the waiting times at the first veterinary office in minutes, right? So first I need to find the difference. Just do a straight subtraction of the data value minus the mean. Remember that the mean was 22 minutes already calculated. So that's my X bar. Right? So here's all my differences. 14 minus 22, negative 8. 17 minus 22, negative 5. 18 minus 22, negative 4. 19, negative 3. 20, negative 2. 24, positive 2. 24, positive 2. 30, 8. 32, 10. Right? That just take the straight subtraction of X minus X bar. Okay, let's square them all. 64, 25, 16, 9, 4, 4, 4, 64, and 100. Okay. Now we need to add them up. Right? The sum from I equals 1 to 9 of the X minus X bar squared. That's the sum of that list. So 64 with the handheld calculator, 25. 64 plus 25 plus 16 plus 9 plus 4 plus 4 plus 4 plus 64 plus 100. So I'm getting a sum which is equal to 290. Now, in order to account for the fact that I added up 9 terms to get that, I divide by 9. I should have said 9 there. 9. Divided by 9. 32.2 repeating. Now, if I had units on there, that would be in minutes squared, right? Because I had squared every one of those differences. Okay, so the last step is take the square root. The square root of 32.2, repeating. 5.68. Rounded to 2 decimal places. Look at that. Okay. Good, Caitlin. Right, so try to do the same thing with those data values right there. So there's your, if you worked it out, you first take the differences, right? Get all these crazy numbers. Then you square them all. Then you add them up. It should have been 144.4. Exactly. Okay. All right, that's the sum of the x minus x bar squared. Okay, now you got to divide by how many terms were there. There was 10. 14.44. Now, because what you've really got, that's actually another statistic which is fairly important. It's called variance. Right? The variance is 14.44. That's like the minutes squared. You need to turn it back into minutes, so you take the square root, 3.8. So I would say a small fraction of people got it in here exactly. And like I said, they didn't even have the formula on the sheet. So clearly you're not expected to be able to do this by hand. But at least by doing it by hand once, you kind of get the understanding of what's behind the standard deviation. Okay, here's how you do it actually with the calculator. Right? First, you go stat edit, which we did before, right? And you only got one list of numbers. They might be in there already because whoever had your calculator last. They might have been doing the homework problems with them, so maybe it's different. So you might want to clear your list. But go into stat edit and put your values under L1, okay? And then you do stat calc 1, and you'll have to hit enter 3 times. And you should see this. You'll have to scroll down to see what's below the n equals 11. Actually, that might not be those values. That's not those values. So don't. In fact, just so I've got the same thing, I guess I better put it in. Second plus 7, 1, 2. Stat, enter. Okay, what are these values again? So I have to go 8, 4, 8, 12, 15, 3, 2, 6, 9, 8, and 7. Right, you put them in, then you go stat calc 1, and you hit enter 3 times. Right, so there's the first thing in your list. There's your mean, x bar. Right, so the calculator is using x bar, not mu, but you know on your formula sheet you got to understand that's the same thing. The sigma is this sigma x. Right, what the calculator is calling sigma is right there. Now the truth is, if you scroll down a little bit, what you're going to see is there's actually a median calculated for you already. There's also got the min, the Q1, the Q3 that we saw in the box and whisker, and the max to get those. Now, right above the sigma x, that Sx, that's actually also standard deviation. And really, appropriately for what we're doing here, we should really be using Sx. But at this level, we really don't. We just use sigma and say that it's all right. Now, the difference between the two is, if you don't know the population's mean, then when you're subtracting the mean I mean, that's still a kind of an unknown to you. You know, you don't have all the values that went into it. You just have your own sample. If you, in the calculation of your standard deviation, every time are using X bar, which was calculated from the same data, then the truth is the standard deviation is supposed to be some like average deviation, like the sum of all the deviations divided by how many deviations there are. But actually there's not n deviations, because when you put in every data value except one, and you've already put it in the X bar, it actually cannot vary in n ways. It can vary in n minus 1 ways. It's called degrees of freedom. And so if you divided the sum, the 144.4 by 9, not by 10, you would have gotten that statistic instead, right? So if you actually know the population mean, you could put it in there, and this sigma x would be the right one. We always just use sigma x. But that's the difference between these two. In a statistics class, you're going to be interested in both of those. You also use the sigma x, like in the next class when we start dealing with the normal curve, right? Now that becomes a model, kind of like the regression lines that we use. Once you start using the model, you consider the mean that it's giving you to be, you know, like the population model, so you use sigma. But if you're using an X bar that you calculated with the data that you're doing here, then you have to use SX. If you get into statistics, if you take AP Stats, then you might see that. So you're competing in an air hockey tournament. The winning, okay, I didn't read the first thing. I should have read it back. If you have like one data value, which you should call a datum actually, which is a lot different than the rest, that's called an outlier. Kind of like when I said, what if you had like one waiting time that was 100 minutes and all the rest were like packed around 20, you know? That's an outlier. And when there's an outlier, I mean, understand if as a statistician, if you are in that kind of a role, this is me talking, somebody has asked you to calculate some statistics. That somebody is probably somewhat of a decision maker. They're the ones who have to decide how they're going to use the data that you're giving them. You might give them the advice, but because you're not quite sure whether that 100 minutes is meaningful or not, whether it was just a fluke and it's never going to happen again, or it's actually something that happens at this place, if you collect enough data, you'd see it happen a lot. Usually the statistician would calculate the mean, standard deviation, and all the relevant statistics with the outlier in and with the outlier out. And then you're handing that data off to somebody else who's got to make the decision what he wants to do with that. I mean, you might advise, but ultimately you're probably not the one who's making the decision. If you are, you're probably not doing your own statistics. You've got somebody else doing that for you. So if there's a value that's a lot different than the rest, then calculate your mean and standard deviation twice. Once with it in, once with it out. So, and your two homework problems that you're going to do, only two, it's this exact kind of scenario. You'll be given an outlier and you'll do it twice. Once with it in, once with it out. Okay, so you're competing in an air hockey tournament. Does anybody do that anymore? Play air hockey? Yeah. And that was pretty big in the 70s and that. The winning scores for the first 10 games were, there they are. The winning score for the next game was 3. Okay, that would be considered to be somewhat of an outlier, right? Not really representative, similar to the other scores. So calculate the mean and standard deviation with and without the outlier. Okay, so let's do that. Right, so I'm going to say with and without. Mean, let me use the right. Mean, I'll call X bar, and sigma. So here, there's going to be a little bit of a table. And I'm doing it with the calculator. Okay, so and I think I've already loaded the data in my calculator, so that it won't take long. Okay, file, open, and we are opening A. I think A is without. So there's the data values. They end with 13. I don't have the 3 on the end. So now I need to calculate the statistics Again, what are the steps? Stat Calc 1. Enter, enter, enter. Right? It looks like the mean. You got an error? Just a second. The mean is 14. And the standard deviation, oh, that was in the wrong column. Back to this. The mean was 14, and the standard deviation was 1.67. Stat, edit. What's in there? Okay, then do your stat calc. 1, enter. Valid dimensions. A lot of times that happens. You just have to clear the memory. Try it again. Second plus 712. Okay, then I'm just going to add a 3 to the list. And obviously it's going to change. Should bring the mean down, and it'll probably make the spread more. Right? Stat calc 1. Now the mean is 13. Now the standard deviation is 3.54. So it made the spread a lot more. Mean was a little bit less. Again, if you were doing stats for somebody, you just do them both. Don't make the decision yourself on whether you should include it or not. Let them make the call which one they want to use. Okay, last thing, z-score, which I think you did a little bit of z-scores before, right? Again, we're interested in z-scores more than anything because it's going to be important to the normal distribution. But on your formula sheet, you have a formula for it, right? And it's using mu and sigma, those notations, right? The x is a data value, right? That's just an individual value. You know what the mu is, you know what the sigma is. Do that math and you get a z-score. It's literally the number of standard deviations from the mean, right? You're taking the x minus mu, that's telling you how far away from the mean you are. Dividing by sigma chops it into intervals of the standard deviation, right? So it'll tell us how many standard deviations are we from the mean. Good. Fine, it's early. Oh, what is it, 1:30? Early. So here's an example of it. 25 students are in a chemistry class to take a test. The mean score is 80% with a standard deviation of 5. You scored 90. What's your z-score? Okay, so we're going to use this formula. Z equals x, that's going to be the 90, minus the mean divided by the standard deviation of 5. Right? So the test was 90, the mean was 80, the standard deviation was 5. Right? So the difference was 10, and then you divide by the standard deviation, 5, so that tells you the number of standard deviations from the mean you were 2. You were plus 2. Right? In a different group of 25 students, which I guess includes you again, it's a math analysis class, and the average score is 75, right? You scored the standard deviation of 3. You scored 84, which is not as good as the 90 you scored on the other test, right? But let's calculate the z-score. Z equals 84 minus 75 divided by 3, right? So it's 9 away from the mean. And then you divide by the standard deviation, that means it's 3 standard deviations above the mean. So in which test did you actually do better relative to your classmates? The second one, you were 3 standard deviations better than the other one, right? So he's better in the math analysis class. Come on. Now, z-scores then are good. They're good for comparing. When you're trying to compare things that are like kind of don't seem similar at all, the way that you can like make them on the same scale is to calculate a z-score. For example, if I was doing a, let's say in the Olympics, that there's lots of different events. One guy's doing the shot put, right? His result is going to be the number of feet that he puts the shot, right? Somebody else is running in the 110-meter hurdles, okay, and their time is going to be in seconds. How do you tell which is really a good performance? In fact, on one of them having a positive z-score means you did better than everybody else. If you have a positive z-score in the race, you did worse than everybody else, right? But calculating z-scores will be able to tell like how remarkable was each of the performances. Then you can actually directly compare them to each other. So that's what z-scores are good for. Okay, so that's actually the end. I've searched long and hard to find some good z-score kind of problems. I didn't find much. I might end up having something like a worksheet next class, but we'll see. That is the end of it. And like I say, next class we will be using standard deviation. Standard deviation. That's not right. Standard deviation and z-scores when we learn about the normal distribution. And that's kind of like the end of all the Algebra 2 curriculum that goes into the SOL. Then we're done, right? We're done. And there's just 2 homework problems. They're both going to be calculate the statistics with the outlier and without the outlier.